Okay, guys, we are going to start today the notes, the official notes, because we haven't even started taking notes on this particular chapter on Unit 8, the periodic trends. So far what you've done is a bunch of different activities with periodic trends, and hopefully you can see that there are some trends that emerge amongst the periodic table and all the families that are on the periodic table, and we're going to discuss them a little further. So we'll get into some more specific trends later, like atomic radius and electronegativity and some other things that are a little more intense and explain why. But today we're just going to talk basics about the outline of the periodic table and the families and what some properties of them. Set a timer for 35 minutes.
Okay, 35
make
minutes
sure that I don't
counting.
go over. So one thing that I would have out if I were you is your big periodic table. I'm going to refer back to this quite often. So if you have your big periodic table out, you can actually look at it. I know that we have the one in the room, but not everybody can see that one. So take out your big periodic table. When we are doing this, you'll want to open up the notes slides if you want. Obviously, I know some of you like to take notes digitally, and it might be a little bit tricky to take notes digitally, flip-flopping back and forth from what I'm writing and what you're typing. So obviously taking notes by hand might be a little bit easier in this particular case, but it's completely up to you. Okay, so you can open up the note slides if you want, or you can just follow along and take notes by hand. So periodic trends and periodic law. Okay, so there were two guys that contributed to the original, what we know as the periodic table that we see today. The first guy is Mendeleev. He helped contribute to the periodic table and most of the design of it, and then Moseley came along and solidified the ideas of what the periodic table looks like and for what we know it as today. So Mendeleev had the periodic table first organized by increasing atomic mass. He first organized the periodic table by increasing atomic mass, which totally made sense. You would think as the periodic table is laid out, increasing atomic mass would make sense. However, if you take a look at your big periodic table, can you find some elements? So if you're looking at the periodic table on the wall, it's the number in red. If you're looking at your big periodic table that I gave you, it's the number in red in the top right corner. They're just in a different place, but they're the numbers in red. And almost all of them, when you go and look at that number in red, it increases as you're going through the periodic table. But there are a couple of them that you'll notice that stand out where the atomic mass does not increase as you're going through the periodic table. It actually flops back down, goes down a little bit, and then jumps back up. Go through and look at your red numbers and see if you can pick out any elements that do not follow what Mendeleev said the periodic table should be designed as. So two elements that don't follow suit of that stand out right away, but obviously there's other ones, is cobalt and nickel. So cobalt has an atomic mass that is larger than nickel, even though nickel comes after it. So those two are two that if Mendeleev had his first periodic table, they probably would have been flipped. So that's just one example. There are others on the periodic table, but he had a really good idea, and he had most things in the correct order. So what did he do once he had this? He came across a lot of things. He came across the fact that a lot of families had similar properties. So when he designed it this way, there were a lot of columns. So he saw trends in the families. What we know as the families today are the columns on the periodic table. And another thing that was interesting about what he did was he saw there were holes for missing elements. I'm going to put that in quotes, missing elements. And those missing elements were just the elements that just had not been placed on the periodic table or discovered yet. They were there, but it predicted the existence, which was pretty cool, of elements that we didn't know about at the time. So, of course, we know Mendeleev wasn't right. So the next guy that came along, Moseley, he studied a little bit more about it. He looked at he looked at the spectra of 38 elements. And from the spectra of 38 elements, he placed them on the periodic table and found out that periodic tables should not be ordered by increasing atomic mass, but it should be, he found better trends in the elements when they were ordered in increasing atomic number, which we know is the number of protons. So better trends emerged when the elements, oh my goodness, my spelling, guys, or my typing, were arranged by increasing number of protons, which we know is atomic number. Now, what I mean by he looked at the spectra, do you know what that is? When we did the spectra flame test. So he basically just burned elements and looked at the colors that came out whenever they burned. And that's how he found that if you arrange the periodic table by increasing number of protons, then you really saw distinct trends come out in the families. So he kind of solidified the idea of what we know as the modern periodic table now. So the modern periodic table, of course, we know is arranged by increasing atomic number. Arranged by atomic number. And then from this, families emerge. Families or columns on the periodic table where properties are shared amongst those families. Periodic law just basically says this. So there's a formal definition of periodic law. It says physical and chemical properties of elements are periodic functions of their atomic number. Are periodic functions of their atomic number. So that's just basically solidifying the idea of if you arrange them in increasing atomic number, you will get this beautiful display of physical and chemical property trends on the periodic table. And that's what we're going to talk about today, is all of the physical and chemical properties that emerge in the families on the periodic table. So, of course, there were a lot of holes in both of their periodic tables. And so what were some of the last elements to be discovered? Of course, because we watched that video, we know that a lot of the radioactive elements were the last ones to be discovered or even created if they were synthesized. But the last elements on the basic foundation of the periodic table to be discovered were the noble gases. So noble gases, and I'm sure that you can maybe guess why the noble gases were the last ones to be discovered. They are extremely unreactive. So they don't react with a lot of things. They don't play well with others. They're extremely unreactive and very rare in nature. So they don't occur, excuse me, in nature just floating around like oxygen does or nitrogen does or iron or all of the other elements that we see in our everyday lives. So just to expand on that a little bit more, helium and argon were the first to be discovered of the noble gases, and then came krypton and xenon. I don't really know, to be honest, where neon fits in. And xenon were discovered later on. So once scientists realized that these unreactive, rare elements were there, it created spelling error. It created a whole family. So I think once they discovered the first one, they were probably like, oh my gosh, there's this whole other column. There's got to be a whole bunch of other elements that fit in there. And so that was probably exciting for scientists to be able to discover all of the different noble gases in that family, knowing that they're there. And then, of course, in addition to the noble gases being the last, the lanthanides and the actinides, those bottom two rows on the periodic table that are hidden down below the main periodic table that we know, those were very much later yet than the noble gases, because the whole entire lanthanides, even though they exist in nature, the actinides were only the first four were in existence in nature, and so they had to be created. So that's why they came so much later. Okay, so one thing that is why this chapter comes after electron configuration is because the electron configuration of a lot of elements on the periodic table, they contribute to our understanding of the properties that exist. And if we just look at the electron configuration, we can see why they react, certain families react with other families, or why certain families are unreactive, or why they have the properties that they do. So electron configuration really explains a lot. And there's something called periodicity on the periodic table within the families, and I want to show you what this is. So I'm going to write this out as best I can. So we're going to look at group 1 and group 18. So the first group and the last group on the periodic table, and we're going to see what periodicity is and these trends that emerge, and it happens all over the periodic table. So excluding hydrogen, because it's just an oddball, group 1 is lithium, sodium, potassium, rubidium, cesium, francium. Lithium, sodium, potassium, rubidium, cesium, and francium. And then group 18 is, we're going to start with helium. I know I said hydrogen was an oddball. Helium's not that different, but it is. Helium, neon, argon, krypton, xenon, and radon. Okay, so we're going to list the atomic number of these things. So lithium is 3, sodium is 11, potassium 19, 37, cesium is 55, and francium is 87. And then same with group 18. We have helium is 2, neon is 10, argon 18, and we're just listing how many protons these elements have. Krypton is 36, xenon is 54, and radon is 86. Okay, so what I want you to figure out is between lithium and sodium, how many is that? How many electrons are added from lithium in that particular row to the next row? Well, that's 8. Obviously, there's 8 electron difference. Well, how about between sodium and potassium? Between sodium and potassium, there's also 8. Now, how about between potassium and rubidium? That's 18. Between rubidium and cesium, if you subtract those numbers, you get 18. And then between cesium and francium, you get 32. Yeah. Make sure I did that right. Now, let's look at group 18. Between helium and neon, how many electrons are added between helium and neon? Of course, 8. And then between neon and argon, 8. So you see what's happening here. Between argon and krypton, 18. Between xenon and krypton, 18. And then between the last two, 32. So we have the same addition of electrons from one row on the periodic table to the next row. This is called periodicity, and this happens throughout the entire periodic table. That addition of that X amount of electrons that stays consistent is why properties can be the same. And this number of electrons is important as well. And we'll talk about all of these as we go through the different families. Okay, so we're going to start with the blocks of the periodic table and study them as a family. So whenever I'm referring to this, what I'm meaning, and I hope you remember this, remember on the periodic table, this was the S block, this entire section right here, and we put helium over here with it. Remember, we wrote helium in. This is the S block. This was from your little colored periodic table. The S block on the periodic table, because there are 2 columns, represents the 2 electrons in the S orbital. So the S block. The S block on the periodic table is just group 1 and group 2. Okay, get my text here. These are chemically reactive metals. Chemically reactive metals. So the first 2 groups on the periodic table, the alkali metals is the first group, and the alkaline earth metals is the second group. They're super reactive. One more than the other, actually. Group 1 more than group 2. a little bit anyway. And so just looking specifically at group 1. So group 1, if I look at, and hopefully you remember this from when we were doing this is the S block. This is S1 in the first column and S2 in the second column. So if I'm writing electron configuration for hydrogen, lithium, sodium, potassium, rubidium, cesium, or francium, anything in that first column, this is what it would look like. The electron configuration would be 1s1, or for the next element it would be 2s1, or for the next element it would be 3s1. That would be the final part of the electron configuration. You can see the trend for S1. So what I'm seeing here whenever this emerges is that because an s orbital can hold two electrons, and it only has one electron in it, it wants the other one to fill up the orbital. So in group 1, in the alkali metals with sodium or lithium, sodium, potassium, rubidium, they only have one electron, and that electron either wants to be given off and given away to somebody else, or it wants to combine with something more stable, because one electron is not a good thing. Everything in nature wants a full 8 electrons in its outer shell. This is called the octet rule. Let's put a little note over here about it. Octet rule. All things want 8 electrons. The octet rule says that if there is a number up here at the top that is not 8, which we have a bunch of numbers that are not 8, that element wants more. It wants a full 8. So it's either going to try and get rid of the electrons, or it's going to try and take a whole bunch of electrons. Well, obviously in this particular case, it would be a lot easier to give away 1 electron than it would be to gain 7 electrons. So let's put that not full s orbital, but it wants a full s orbital, needs 1 electron to fill that orbital, technically, and then it would have a full s orbital. So it wants to react with other things. It wants to combine with other things. So some properties of alkali metals, and they are extremely reactive. They are the most reactive metals on the periodic table because of that 1 electron. That's really all that happens. The top, a little less reactive, like lithium and sodium, and they're not so bad. They're really reactive, but not so bad. Potassium is crazy, and rubidium, cesium, francium are like explosive reactive. So as you move down the column, you get even more crazy with their reactivity with things. So let's do some properties here. So group 1, alkali metals are silvery in appearance. They can be cut with a knife. This is a really weird one. A lot of the cut with a knife. You can take a lot of the alkali metals out of the container. They come in a container that's stored in kerosene, so they don't react with the air. They have to be like surrounded by a liquid in order to not react with the air, like oxidize with the air. And you can take them out and you can just slice them like butter with a knife, which is really odd because most metals, you think you wouldn't be able to take the metal on the bottom of your chair that you're sitting on right now and cut it with a knife. It's just too hard. But they are actually very soft, and they get more soft and have lower melting points as you move down the column. They're not found pure in nature. The reason why is because any water that touches them or water vapor that's in the air reacts with it vigorously, which is our next thing. Reacts vigorously with H2O to make hydrogen gas. If you know anything about hydrogen gas, like the Hindenburg, it is extremely explosive. So any little bit of heat or flame, and obviously water is present in our world all the time. So this is a reason why they're not found pure in nature, because they would react with the water in the air and then they would be exploding all over the place. So they combine with things instead of being pure in nature. They're stored in kerosene, like I said, not necessarily we need to put that down. And down the column, they have lower melting points, MP melting points. Write it out if you're not going to remember what MP is. So they become softer and more reactive as you move down the column. So those are the alkali metals. Group 2, the next group over, beryllium, magnesium, calcium, strontium, barium, and radium. These are called the alkaline earth metals. So if we're going back to the electron configuration. So if we look at our Again, if you remember this, the second column is filling up the second spot in the s orbital. So if we're writing electron configuration for any of those elements, it would look like this. It would be 1s2, or it would be 2s2, or 3s2. This is the ending part of those electron configurations. So what we have now is we have an s orbital that is full, which is nice, but the octet rule still applies. Things still want 8 electrons, and we are not even close to 8. We only have 2. So they're still going to want to give away those 2 electrons or combine with something else in order to form stability with those 2 electrons to get 8. So these are reactive, but they're not quite as reactive as the alkali metals. So we're going to put over here as a note, they have a full s orbital. So we're going to say they are a bit more stable than group 1. But not so much that they're not going to react with things. So let's talk about some properties of the alkaline earth metals. They have 1 pair of electrons for reacting. So instead of just having 1 electron, which generally tends to just leave the atom with the alkali metals and just go away and then everybody's happy, this is a pair of electrons. So they're really more about sharing a little bit than the alkali metals are, because they can share a pair of electrons, like, hey, I have a pair of electrons to contribute to gain full octet. They are harder than the alkali metals, denser than the alkali metals, and stronger. So anything that I put in here with like more than, I'm referring back to the first group on the periodic table. So they're harder, denser, and stronger than group 1, or the alkali metals. They have higher melting points. Higher melting points. Again, higher melting points than the alkali metals. And they're not found pure in nature. Not found pure in nature. These also can be reactive with things in the air and reactive with other stuff that floats by. So you're not just going to find magnesium, calcium hanging around out in nature, because fire and heat and oxygen and water all cause things to happen to these. And we'll do a lab, probably not until we get back from Christmas break, where we'll study the reactivity of these different metals and put some of them in water and see what happens whenever they react vigorously. Okay, so that's the alkali metals and the alkaline earth metals. That takes care of all the families in the S block because there's only 2 columns. But then there's those 2 oddballs, right? Hydrogen and helium, which are like the odd family members that kind of belong to the family, but you're confused because they don't look like or act like anybody else in the family. We all know who that is. Okay. So one of the things that I like to do is explain the fact that hydrogen and helium, even though we, like, remember we kind of drew helium over here, as far as the properties go, hydrogen is nothing like its family it belongs to. It is not a metal. It's not shiny. It's not reactive to water. None of the things follow suit with. It's not easy to cut. It's not even a solid. It's a gas, obviously. So, and then helium, similarly, it's not like the alkaline earth metal. So the only reason why we put it over there was for purpose of electron configuration. So we're going to forget that idea just for a minute. And what we're going to do is we're actually going to put and think about hydrogen as being over here. That was terrible. Of course, we know that helium is like the noble gases because it has a full shell and it's super stable. Hydrogen has properties that are very similar to group 17 on the periodic table. Fluorine, chlorine, bromine, iodine, astatine. It's got more of properties like that. Those ones want 1 electron. We'll talk about that in a bit. They want 1 electron just like hydrogen wants 1 electron. So let's talk and make some notes a little bit about hydrogen and helium. Hydrogen. You should keep a tally of how many typing errors I make. And take bets. Don't bet. It's gambling in school. Okay. Yeah, we gamble anyways with the card thing. Might as well just do whatever. Okay. Hydrogen is not the same as group 1. So that's what we just said. It's not like the rest of the alkali metals. Hydrogen is unique because it is what we call diatomic in when it occurs in nature, meaning it is written like this. H2. We don't just see an H floating around. There's no H's just floating around in the air ever by themselves. They like to pair up with another one of themselves, mainly because they only have one electron. But another hydrogen only has one electron too, and if they combine together, they have a full s orbital because there's each one of them contributes to fill that. So diatomics, I don't know if you learned anything about diatomics. Maybe depending on who you had for freshman science, they may have used an acronym. We used Brinkelhoff, but maybe if you've ever heard of H. Broncliffe, that is an acronym for learning all the diatomics. H. Broncliffe obviously has an H in it, so that's why it has a 2. Anyway, diatomic just means they travel in pairs. And we're going to put a note about it acts like group 17, the second to last group on the periodic table. So they're called the halogens, which we'll discuss that in a little bit. So then we have helium. Helium has a full outer shell, so it is a lot like all the rest of the noble gases where it's stable and happy. It has a full s orbital. And because helium only has that s orbital, it's one of the weird elements. It doesn't want 8. It's like the only element besides hydrogen really that doesn't follow the octet because it doesn't have a p orbital floating around it. It just has an s orbital. And as soon as the 2 electrons are in the s orbital, it has a full outer shell. So it's a little bit of an exception to the octet. It is stable in nature. So it's completely fine just floating around by itself. That's why it was so hard to be discovered. And it is very non-reactive. Non-reactive. Okay. So they're the only ones in those columns. They're the only oddball elements on the periodic table. Okay, so let's dive into this group on the periodic table. Remember, that was the S block over here. And then the P block was over here, but we're not there yet. This is the D block. Remember, the D orbital has 5 clover leaves, but they can each hold 2. So this is the D block and holds 10 electrons total in it. It can hold up to 10 electrons, I should say. Okay. The D block on the periodic table is groups 3 through 12. So it's chucked right there in the center of the periodic table. We're going to put here that it can hold up to 10 electrons in this particular block of the periodic table. And these are called the transition metals. This whole section of elements is called the transition metals. They all are. So iron, cobalt, zinc, gallium, silver, gold, mercury, all of the elements there are transition metals. There's actually a little bit of a spew over into the P block of a couple of elements. So these are all the transition metals, all of them. And then also tin and lead are considered transition metals. I don't know. They just fell out of that section or something. So tin and lead are also part of the transition metal. They're not really part of the D block, but they're part of this category we call transition metals. So talking about some properties of transition metals. They have, obviously, we studied this beginning of the year, I feel like, metals and non-metal properties like ductile and malleable. They have typical metallic properties. They are good heat and electricity conductors, obviously, because that's like a lot of the metals. They're less reactive than the first 2 groups. So they are considered metals. Obviously, they're called transition metals, but they are less reactive. I'm checking my time here. Sorry. Okay. They don't want to explode when you put them in water. They don't produce hydrogen gas that's super explosive whenever they react with things. So they are less reactive than groups 1 and 2. So they're way more stable just being themselves in nature. They do like to combine with things, but they don't always combine with stuff. Some do not form compounds at all, actually. Some do not form compounds. They are okay alone. So there are some elements on the periodic table that don't even like to, I wanted to get an example of this, that don't even like to form, like, for example, gold. Gold is totally stable and happy by itself. Platinum is also another element. They just aren't going to form. Now, you might think like, well, then what's like 10 karat gold versus 20 karat gold? Do you know the difference then? Because obviously there's different forms of gold. It's not gold combining with other things chemically. Do you know what that's called when it's not chemically combined but just mixed in? It's called an alloy. So the ones that are okay being alone and are happy and stable and perfectly fine, like if you have pure gold jewelry or gold jewelry at all, it doesn't tend to get really nasty or have anything happen to it. You can get tarnishing on it, but that's really just not really even with gold. That's why our jewelry is made of that. It doesn't react with things in nature. But there are some transition metals that do react with other stuff, and we'll learn that when we start learning about different compounds. Okay, then there's the P block. The P block, of course, is this section on the periodic table. This is a super unique and probably the most diverse family section on the periodic table. This is the P block. Remember, it corresponds with the p orbital. There are 3 dumbbells in the p orbital having 2 electrons each in them, so the p orbital can hold up to 6 electrons. Can hold up to 6 electrons. But remember, this is in addition to the 2 that are already in the s orbital. So technically, this section of the periodic table is one of the more stable sections because it's actually 3 through 8 electrons. So we're getting into that territory of things that are approaching a full octet. Can hold up to 6 electrons, but have 3 to 8 outer shell electrons. Okay, so together, the P block with the S block form what is called the main group elements. And when you were doing that super fun activity where you cut out the tiny little squares and pasted them all together, these were all of the main group elements that you were putting on the periodic table. So what I want to show you is the main group elements consist of this section right here and this section right here. So the S block and the P block. Those are called the main group elements. The transition elements here are not main group elements, and neither are the intertransition metals, the lanthanides and actinides. Main group elements are S and P orbital elements only. Main group elements, S and P block elements. Okay, so the P block, let's go back to that because I just wanted to tell you what the main group elements were. Back to the P block, this section just over here, right? This is the P block. They have the most diversity in them. So it contains all of the nonmetals on the periodic table if we ghost hydrogen over there into that section. I'm up here with the P block. Contains all of the nonmetals, some metals, and all of the metalloids. So it is a very unique mixture of things. It's got solids, liquids, and gases in it. It's got all the metals, nonmetals, and metalloids in it. Not all of the metals, obviously, but it's just a very fun mix of elements on the periodic table. So the metalloids are this strip of elements along the metalloids are here. So metalloids are along this zigzaggy line right here. They sit between the metals, which are over here, and the non-metals, which are over here, is this group called the metalloids, and it hangs out right in between. And they have characteristics of both metals and non-metals. Okay, so let's list the metalloids. There's 7 of them. There's boron, not lowercase b, boron, silicon, germanium, tin, nope, arsenic. Sorry, I was doing our lab. Arsenic, antimony, tellurium, and polonium. Those are the 7 metalloids. They are semiconductors, which is what makes them super unique and useful in technology stuff, engineering. You guys who make all of your engineering parts, all the tiny little things that you're soldering onto your circuit boards, those, a lot of them contain metalloids. So they are semiconductors. They are brittle, solids. All of them are solids, and they have metallic. There's our timer. Oh, capitalized. Metallic and non-metallic properties. And they are somewhat conductive. They do conduct electricity very well. We're going to put that because that's what makes them super unique. Conduct electricity, but not heat. So you want your computer parts and your cell phone parts to conduct electricity really well and be really efficient, but you don't want them to be conducting heat and melting in your pocket. Okay. I really wanted to get through this last thing, but I feel like we're running out of time. Just a couple more minutes. Let's get through this last slide. Okay, so looking at the P block a little bit more, there's that group, the second to last column. So noble gases, right? Noble gases are those ones that are really stable and have a full outer shell. But one row over is this group called the halogens. So this group right here on the periodic table, these are the halogens. It's where we put hydrogen in at the top of that group. Halogens have 7 electrons in their outer shell. Remember, everything wants 8 though, so they want 1 electron. They are searching for 1 electron. Well, who has 1 electron? The alkali metals. So P block halogens generally tend to combine or share or exchange or take from the alkali metals. And that's what makes them unique and makes them a good match for things in the first 2 groups on the periodic table. They will also obviously gladly take 2 electrons. 2 separate elements, atoms will take 2 electrons from the alkaline earth metals, but they combine a lot with those first 2 groups. So these are the most reactive nonmetals on the periodic table. They react with metals to form salts. So just think about for a second, look at the periodic table. If we took sodium, which is an alkali metal, and combined it with chlorine, which is a halogen, what do we get? NaCl. We get a salt. Now, when we say salt, we're not always referring to table salt, NaCl. You can have any salt. You could have KCl or LiCl. These are all salts too, just combinations of a metal and a nonmetal from opposite sides of the periodic table. So they are 1 electron short of a full octet. And they are super unique. I'm going to write this last part in, and this will be our last thing. They're super unique because this family of elements has the most diversity on all the families. So fluorine and chlorine are the 2 gases. Bromine is this brownish red liquid at room temperature, and then iodine is a solid, and astatine is actually synthetic, man-made, but it is, of course, a solid as well. So we have solids, liquids, and gases just within this family that all have similar properties to each other, and they react the same way chemically, but they're totally different states of matter. And then we'll talk about the lanthanides and actinides a little bit later. They're just a unique group of elements on the bottom of the periodic table that most of them had to be, well, half of them had to be created by humans. So, okay. If you are in period 3 right now, go ahead back to the agenda. It'll tell you what to do for the second period. If you're in period 5, I will see you tomorrow.